Yeah. Gotta get my brain going. Okay. Crew. She's all cool. Okay, folks, I showed that it is that time of the day. So I am going to go ahead and get started by first passing around the sign-in sheet. Now, I am going to make a suggestion simply because this past fall, that's what it was, it sometimes hit one side of the room and missed the other side of the room. So why don't we do it this way? I'll start it here, and then we'll go all the way through the front. Then you can pass it back and go all the way back up that section, and then come back this way, so that we don't have to worry about it missing anything.
I say we make it into a paper airplane, just throw it.
Yeah. Then it will still miss something. I mean, greater probability. Okay, so now you're going to actually see somewhat my style on the lectures. I am going to do my best every single day to start out with any announcements to kind of remind you what's coming up, what's new, even though, yes ma'am, I know that it is on Blackboard, it is still good to discuss it. But so, as a reminder, there is no lab tomorrow. You're good there. We will really pick up with lab starting the next week. You do have a Vesper quiz due that on Sunday at 11:59 p.m. And I've gotten several questions about my notation of B plus N. That just means bonding groups and non-bonding groups. So in other words, your groups that are bonded to the central atom and your lone pairs. Also on Sunday, you will have a homework that is due. Now, I wanted to put in the parentheses this adaptive follow-up. Because I do use active chemistry, I have the opportunity to do what's called adaptive follow-up. Now, adaptive follow-ups do not actually impact your grade directly. However, if you completely botch a homework assignment, you can do the adaptive follow-up and it may give you more experience with that type of problem. So that you can maybe pick up some of the pick up and learn some of the mistakes you missed. But what I'm trying to get at is I do not require the adaptive follow-up. It is there. But it is not part of your grade. It is not required. It is there for students that need that lecture. Okay, so your first quiz is going to be on Monday. I open it on Monday, it closes on Monday. And I will remind you on Monday. But it's going to be over the material we're covering today. Now, the other question is, when are you in your office? Because you made quiz 1 due by turning it into your office. So I looked at my schedule, and these are the times I will be in my office between now and next Friday. Now, I do have one note to make. Unfortunately, due to scheduling things over the holiday break and way last fall. I am gonna miss my 2 office hours next week due to doctor's appointments. But I will be in my office all of those times. So I'm gonna be in my office all day Friday, for instance, of next week. And then the next note was for me, sign-in sheet, which I'm very glad to see a few people remember their cards. And I did not bring mine with me. I can go grab them real quick. If I can get most of them, yes. Oh. Luna, can you be nice and let me run and get them? They're sitting on my desk.
Yeah, PPA, but when I'm done here,
Very easy. I had them here. I just picked them up.
it was.
Thank you. They are, but I'm not sure exactly. I'm missing one. Okie dokie. So let me just remind everybody where life stands in chemistry. You started out college chemistry 1 with some potentially some review of some of the mathematics associated with chemistry, but then you quickly got into discussing the elements and what an atom of an element looks like. And you went in and you figured out the number of protons in an atom of an element. And you talked about isotopes, figured out the number of neutrons in an atom of an element. And then you talked about the electron configuration, so you could determine where every single electron in an atom of an element resided. Then, after you had a complete understanding of the atoms and the elements, which by the way is a chemist's alphabet, you then started combining our alphabet to form compounds. And you were introduced to ionic compounds and covalent molecules. Ionic compounds contain ionic bonds, which is an electrostatic attraction between the cation and the anion. Whereas covalent molecules contain covalent bonds, which is the result of the sharing of electrons between 2 atomic nuclei. Now, after you did that, you really got into naming those compounds. And then you got into Lewis structures, where you started understanding the connectivity of all of these atoms. So you went from our alphabet to our words, which is the chemical formula. with anything in English, you take words and you start combining them to form sentences. For a chemist, those sentences are balanced chemical equations. And with those balanced chemical equations, you started talking about how to predict the states of matter of the materials in the balanced chemical equation, specifically that of ionic compounds, where you use the solubility rules, or potentially with acid-base neutralization reactions. You also talked about redox reactions and maybe some gas evolving reactions, depending upon the class. But if you're going to talk about a chemical reaction, you can't only talk about the identity of the reactants and the identity of the products. You can't simply understand whether they dissociate in water to form a solution or whether they remain intact. If you're going to tell the story, you got to also include the energy associated with reaction. And so you spent chapter 9 talking about enthalpy and calorimetry and that particular pieces of information. So all of that was basically giving you some of the bases into our storyline, our alphabet, our words, and our sentences. Now, after that, we then started going in and looking at these materials in greater detail. What does it mean when we say something is a gas? And you spend an entire chapter on the gases. And then what we'll be picking up with, starting today, is liquids and very briefly, solids. So when we start talking about the states of matter, there are 3 primary states of matter, that being the solid, the liquid, and the gas. Your gas you talked about in College Chemistry 1, chapter 10, and we found out that a gas is going to expand to fill whatever volume is available to it. That when you look at gas molecules compared to the space between them, the molecules themselves are very small compared with the space between them. And because the gas molecules are very small compared with the space between them, gases can easily be compressed. Now, one of the, and it was mentioned, but it may not have been, we may not have gone to it in great detail. But another aspect associated with the molecules being so small compared to the distance between them is that, for the most part, these molecules don't even know each other exist. They don't really sense one another. So if we're talking about intermolecular forces, that means they don't know, there's no intermolecular forces for a gas. Because the term intermolecular forces is kind of like interstate. It is from one to the other. The interstate running, I-40 running between Oklahoma and Arkansas and lots of other things. Interstate intermolecular formula, or intermolecular forces. So with the gas, there is definitely little to no intermolecular forces. Now, the one chapter that we are not going to go much into is that of a solid. That is chapter 12. To be quite honest, in chapter 12, it goes into a lot more detail about what a solid looks like. And for me, as a inorganic chemist, I actually enjoy that chapter, but it is not relevant. It is not necessary. It is relevant. It's not necessary to where we're headed. So I won't be doing that chapter. But if you simply look at a solid, what you'll notice is that its molecules are extremely close together. They are stuck essentially in place. All those molecules can do is basically do a little bit of vibration. They're not going to move very much. And because they're not going to move very much, you can expect to have strong intermolecular forces found within a solid. Now, what our primary discussion is going to be about for chapter 11, though, is going to be the center state of matter, which is that of the liquid. If you look at a liquid, again, those particles are very close together. But unlike a solid, the particles in a liquid are allowed to move around. Now, backing up though to the first statement, they're very close together. Because these particles are very close together, we can expect to have intermolecular forces. We can expect that these particles are going to sense one another. And depending upon the extent of those intermolecular forces will determine how that material behaves.
Does intermolecular forces determine viscosity?
That is exactly where we're going. So there are, is because intermolecular forces, when you think about intermolecular forces control boiling point, melting point, viscosity, vapor pressure, surface tension, they control capillary action. There's a lot of things the intermolecular forces are responsible for. Now, with respect to liquids, there are three primary intermolecular forces that we are going to be working with at this time. And those three forces are going to be London dispersion forces, dipole-dipole forces, and hydrogen bonding forces. Now, when you think about London dispersion forces, every substance has London dispersion forces. London dispersion forces are the result of electron movement causing a temporary dipole. And if you think about if you think about the word dipole, di means two poles, so two poles. So you have a partial positive and you have a partial negative. And in college chemistry 1, when you were talking about molecule polarity or bond polarity, you probably used an arrow notation to indicate that polarity. Folks, even the element xenon in gas form has a dipole moment. Has a London dispersion forces. Carbon dioxide, which you determined was nonpolar in college chemistry 1, it still has London dispersion forces. Now, my best way to explain London dispersion forces is to have a little bit of fun in class. So we're going to do the wave. I'm going to run across the stage and hopefully she doesn't bark at me too much. So when I get to your area, you're going to raise your hands just like you were doing the wave at a game. And then I'm going to explain how that is just like London dispersion forces. Y'all ready? You get started. 1, 2, 3. No beating. That's okay. Okay. Let's talk about how the wave is a lot like London dispersion forces. And folks, this idea came up. I woke up in the middle of the night several years ago with this idea. So yes, chemistry literally haunts my nights. I love it, but it's okay. So when you were in college chemistry 1, you talked about covalent bonds. And covalent bonds occurred where the electrons were in between two atomic nuclei. Atomic nuclei 1 is my toes. Atomic nuclei 2 is my head. Now, we drew sticks to represent these bonds. But folks, sticks is actually a very bad representation of a covalent bond. It's actually a very bad representation. Because when you see a stick, you think nothing's moving there. And that's not how it works. Electrons are in constant motion. So I got my atom 1, I got my atom 2, and I got my electrons. And typically, your electrons hang out in between atom 1 and atom 2. But they're constantly on the motion or on the move. And sometimes they wind up near closer to atom 2. And because electrons are negative, that means this area is negative. They mean positive on the other end. Now, the way London dispersion forces work is when one molecule all of a sudden becomes polarized, it causes the molecule next to it to become polarized. And then as it's relaxing, this one polarizes. As this one's relaxing, this one polarizes, and so on and so forth. So everything contains London dispersion forces, folks, because electrons are always moving. And they will at some point wind up on one side of the atom or one side of the molecule. So that's my quick display of London dispersion forces. So everybody contains those. Now, with respect to our polarity in molecules, this is the only force for nonpolar molecules. The other two types of intermolecular forces has to have a polar molecule. The other two types of intermolecular forces have to have a polar molecule. So we can say all polar molecules will have dipole-dipole. They have dipole-dipole because polar molecules have a permanent pole. They have a permanent positive and negative end. So there's always that dipole moment. Now, the second type of molecule that is going to have a dipole-dipole is going to be also the type of molecule that can have hydrogen bonding. So these are going to be polar molecules. But they have a very specific criteria. In order to fit into the hydrogen bonding criteria, they have to have a specific type of bond. They either have to have an OH bond, or they have to have a NH bond, or they have to have an FH bond. Me either. No. So anyhow, hydrogen bonding is just a subcategory of polar molecules that have a special type of bond present also. So if something has hydrogen bonding, folks, it also has dipole-dipole and it has London dispersion. If something is if something has for a maximum dipole, then it has dipole and London dispersion. But only if it has one of these three bonds would it have the third type of intermolecular force as well. Questions? Yes. Yes. If it has hydrogen bonding, it has all three. If it has dipole, it only has two. Now, folks, again, intermolecular forces is responsible for an element's properties. I mean, a compound's properties, or both. Now, with respect to these intermolecular forces, there is an increase in strength, where London dispersion forces are the weakest of the types of forces. Then you got dipole, and then you got hydrogen bonding. Now, when the forces are all the time, for instance, if I put argon next to krypton, they're both going to have London dispersion. So who's stronger? That's where this second piece comes into play. Because strength increases also with the number of groups and also with increasing length. What I mean by the number of groups is, say I have something that has hydrogen bonding because it has one OH group, but I have another molecule that has two OH groups. Because it has more groups, it's going to be stronger. That's what I mean by groups. It's the same type of group, but there's more than one of them. So again, intermolecular forces determine your properties. And I tried to simplify this as much as possible because if you watch my videos, I talk about viscosity, then I talk about vapor pressure, then I talk about this, then I talk about that. But I tried to combine it all in this one little table. To make life easier on you. And you will notice that it has low intermolecular forces or weaker intermolecular forces. And it's going to be a lower melting point, lower boiling point, lower viscosity, lower capillary action, lower surface tension, and then higher vapor pressure. And the reason the vapor pressure is the oddball has to do with what vapor pressure really means. When we talk about vapor pressure, what we're talking about is we're talking about a closed container of our liquid. And when we talk about vapor pressure, we're talking about how many molecules can actually go into the gas phase. If you have very weak intermolecular forces, a lot of those molecules are going to go into the gas phase without a whole lot of help. And so it's going to have a larger vapor pressure, gases, pressure, because there's more gas molecules bouncing off the walls. Whereas when you have a high intermolecular force, again, you have your liquid, which I'm not going to draw all the molecules like I did on the other one. But if it has strong intermolecular forces, then you're going to have only a few go into the vapor phase. And therefore you have a much lower vapor pressure because you have fewer gas molecules bouncing off the walls of the container. And folks, speak up anytime you have a question. I know I'm rattling rather quickly because, again, this is a flipped classroom style.
If you had a molecule that had a lot of bonds in it, but no hydrogen bonds, versus one small molecule that has one hydrogen bond. Would you have to use formulas to figure out which one was stronger? Like, does that make sense? Like
It-
a long flat one versus just one?
It all depends upon how many, for instance, carbons that long flat one had. Because eventually, I think it's at 5 or 6, and I can't remember the number, carbons in the chain. And it'll have about the same boiling point as water. So it does depend upon how many. Any other questions? Then the next thing we're going to actually do is we're going to be determining IMFs. And we are going to be looking at relative strengths and applying the information I just rattled off. As I said, I wanted to keep it where I have more time for examples. Okay. So you may ask, why did I have you go into the Vesper quiz and do the Vesper quiz? Well, part of that has to do with taking a formula and being able to know whether it's going to be polar or nonpolar. Because folks, if you don't know whether a molecule is polar or nonpolar, can you determine the intermolecular force? No, because that's the foundation. That's the foundation of it all. So you got to know whether it's polar or nonpolar so you can determine the intermolecular force. The reason I had you do the VSEPR is because you got to be able to do Lewis structures. Because if you cannot determine the connectivity of the atoms, then you don't know whether it's going to have an OH bond, an NH bond, or some other bond. So you got to be able to do it. That's why you're required to do the Vespers, because it is directly applicable to what we're doing now. So with CO2, you have your carbon double bond oxygen on both sides. And you would figure out this is a non-polar molecule. Because CO2 is a non-polar molecule, it only has one type of force available to it. And that is what? It has to be London dispersion. Why do you think why do you think carbon dioxide is a gas at room temperature? Because it has weak intermolecular forces. No, I'm saying the molecule. So this molecule is nonpolar. And so if we were to draw this molecule out, we would probably, in a kind of density diagram, we would draw it where it's just a big blob, in my case, which has the C and the O inside it. Now, keep in mind, these electrons are in constant motion. So what would happen is this electron that is spinning in, that is part of this bond. Let's get rid of that one. Let's do it a different way. The electron here that's spinning around, it's going to wind up on this side of the molecule. And when it does so, all of a sudden you have a very temporary dipole where you have a positive end and a negative end. But that is temporary because it quickly goes back to being even throughout. So it is because of this electron movement that we actually have the London dispersion. So it's not the carbon, it's the electrons that are responsible. If we look at HCN, HC triple bond N. If you take the electronegativities of these atoms, hydrogen's at 2.1, carbon's at 2.5, nitrogen's at 3.0. There is an increase in electronegativity towards the nitrogen, so this molecule is polar all the time. So we have a polar molecule in hydrogen cyanide. So we know that everybody has London dispersion. And because it is a polar molecule, we know that it's going to have dipole-dipole. The question is there another force? In this case, no, because it doesn't have an OH bond, an NH bond. It has to be those two atoms side by side. So if I were to compare CO2 and HCN would have the higher melting point and higher boiling point, lower viscosity, and I could continue. Or I'm not lower viscosity, lower vapor pressure. Higher viscosity. By comparing A to B. Yes.
Can you explain? So how can you tell that it has that?
The stronger the intermolecular force, the higher the melting points, boiling points, and so on. So it comes back down to this statement, where if you have London dispersion only, compared to if you have London dispersion and dipole-dipole, because it has that dipole-dipole, it is a stronger force. And then it comes down to, if it's the stronger force, then it's going to have the higher melting points and boiling points. Oh, no, this is on a 4-point scale. The table of electronegativities, fluorine is the actual, is the most electronegative atom with 4.0. You don't have to know the numbers. I'll give you a table of electronegativities, but you can also realize fluorine's the most electronegative, francium's the least, and estimate from there. Okay, folks, the type of formula that you see here is just simply a typical molecular formula. We also have a formula where we write out how the atoms are connected. So I could have written this next formula as C5, or excuse me, 4, C4H10, which is butane. And this one would be written as C4H10O. But as you progress through chemistry, especially as you get into organic chemistry, you're going to see this type of construction a little bit more. If I want to take this construction and move it into Lewis structures, we start with the beginning, and I don't know how many faculty did this in college chemistry 1, and that's why I want to do it. So you start with your carbon that's at the beginning. On that carbon, I'm going to place 3 hydrogens with bonded to the carbon. The next element in line is another carbon. On that second carbon, I need to put 2 hydrogens. Then it's bonded to the third carbon, which needs 2 hydrogens, which is bonded to the fourth carbon, which needs 3 hydrogens. We have just taken this structural formula and moved it towards a Lewis structure. Now, on this next one, you have a carbon bonded to 3 hydrogens, bonded to another carbon, which is bonded to 2 hydrogens, bonded to an oxygen, which is bonded to a carbon to 2 hydrogens. And then you have 3 hydrogens on the last carbon. Now, this is where this type of formula is more challenging. While the carbon hydrogen piece was pretty straightforward, you got to remember how many electrons does a group 2 element always have in a Lewis structure? What rule does it follow? Octet. It needs 8 electrons, and right now that oxygen only had 4. So we had to add 2 lone pairs. Now, you may ask why that's important. That, folks, is important because if I were to take and draw this using VSEPR theory and draw my molecule correctly, what it really means is I have a polar molecule. Huh? It is bent, yes. Which means I have a polar molecule. If you didn't remember your lone pairs, you might not have realized you had a polar molecule, because you would have used it as a linear on that oxygen. Now, what type of forces does the one on the left have? London dispersion. Is that its only force? Yes. Folks, anytime you see nothing but carbon and hydrogen, it's nonpolar. That's its only option. It doesn't matter if it has a double bond or a triple bond. If it's only carbon and hydrogen, it's nonpolar. And what type of force would the one on the right have? I heard all 3. Okay, it's okay. I wanted to make sure we answered this though, because it doesn't have hydrogen bonding because the oxygen is not directly attached to the hydrogen. So even though there's oxygen and hydrogen present, since the hydrogen is not directly bonded to the oxygen, it does not have London. I mean, does not have hydrogen bonding. So again, this one over here would have the higher melting point, higher boiling point, and so on and so forth. And yes, part of what I'm trying to do is teach you how to interpret these formulas written in various ways. So our next one. When you see something in parentheses, it means you look at the number outside the parentheses, and that is telling you how many of the substance within the parentheses is attached directly to the element. This is a condensed formula. It condenses it to make it where you can fit it in just one line, but you got to know how to interpret it. So in this particular case, the nitrogen has 3 CH3 groups. Attached to it. That's what the parentheses is telling you, is that many is attached to this element. Now, once again, the big question. Nitrogen's in period 2. How many electrons must a period 2 element have? 8. So that nitrogen, has a lone pair. And folks, for some of you, I remember to say this. For others, I didn't. I set my alarm because I think we all need about a 2-minute break to just stand and breathe. And then we're going to come back and I'll go to some more problems. This is halfway through class though. So we're going to have a 2-minute break to stand and breathe. I know it's a silly little thing, but I'm going to try this. Yes. She's like, I need to get up. Yeah, I just feel like a stretch break is useful. What's up? Come here. Sit. Good. Yeah, there we go. Okay, folks, it's that time again. Did that help a little? This is the first time I'm trying the 2-minute break at the halfway mark. So to help you a little bit, move. I'm always trying new stuff if I think it'll help students, so. Okay, so going back. We determined that this nitrogen had to have a lone pair because it needs an octet. Therefore, if we were to look at this compound, it would have a trigonal pyramidal shape. And if it has a trigonal pyramidal shape, meaning it looks like a pyramid, what type of polar is it? Polar or non? It's polar. Carbon and hydrogen don't, but the nitrogen in the middle causes it to be polar. Trigonal bipyramidal is not polar as long as all the external atoms are identical. So this, folks, is a polar molecule. So what are we looking at? I heard London dispersion. Dipole, dipole. Anything else? No, because the nitrogen is not directly attached to the hydrogen. Correct. Now, the skeletal structure. These, again, are something you're going to see a lot in organic chemistry. It's organic chemist's favorite way to write things. So, at every point and at every intersection, there is a carbon. So this is a carbon, carbon, fluorine. In skeletal structures, they never show the hydrogens. But how many bonds must carbon always have? 4. So that means that there are actually 3 hydrogens on this carbon, and there are 2 hydrogens on that carbon. And then if I were to finish out the Lewis dot structure, I would need to put lone pairs on my fluorine, which they don't tend to show the lone pairs on the external atoms. It's mostly central. So, yes.
If the skeletal structures never show the hydrogen bonds.
Never show the
The
hydrogens.
hydrogens, correct. Does that mean that if there was any on the fluorine, they would show that?
Yes, it's only on the carbons that they never show the hydrogens. It's only on the carbons that they do not show the hydrogens. It's a very shorthand notation, and it is because chemists and those studying chemistry are supposed to know carbon has to have 4 bonds. So if it's not somebody else, which they would show you, that means it has to be the hydrogen. So what type of forces does this guy, or this molecule have, which by the way is ethyl fluoride? Okay, well, it is going to be polarized towards that fluorine. because fluorine's the most electronegative atom. So what type of forces? So who has the highest melting point and boiling point probably? As my molecules. I talk to animals, I talk to molecules, I talk to, yeah, they're who's.
I'm gonna say the first one because there's more bonds. There's more groups.
Okay. So look back at your note. I'm not gonna answer just yet. Okay, that is true for the fluorine. But they both have the same intermolecular forces. There's another piece of the story here.
Fluorine has more.
So look at the. So who thinks it's going to be my trimethylamine? And no, you don't have to learn how to make them. Who thinks it's going to be the trimethylamine? Folks, it's okay. Who thinks it's going to be the epifluoride? Who is too scared to answer?
I am too confused to answer.
Okay, so what I want to draw your attention to is back here, part 2. You increase the number of groups. And so most likely, the trimethylamine would be considered to be slightly larger. And therefore, or slightly higher intermolecular forces.
One on the left.
Correct.
Okay.
That one's actually a pretty close toss-up, to be honest. But I was wanting to use these concepts here too, because you're going to get into close toss-ups potentially. I want you to be able to think through, okay, it doesn't always have to do with the most electronegative atom. It can also do with size of the molecule.
And I'm sorry, just for a refresher, electronegativity is stronger as it goes up and to the right periodically.
Correct. Fluorine is the most electronegative atom. Francium's the least, which is 87. It's most reactive because of its size, but it does not have anything necessarily to do with the electronegativity. It has to do with size. Okay. So I would have expected this one to have, just from generalizations, folks, keep in mind, when we start saying this one should, we're having to go off of generalizations, because without going in and comparing everything, you're not going to know definitively. But this one should have had higher melting point and boiling point due to size. It's a bigger molecule. Okay. These next ones get back into normal territory. This one is methyl chloride. And this one is tetrachloromethane. And like I said, you don't have to name them until you get to organic chemistry. Both of these molecules are tetrahedral. So the compound on the left, which is methyl chloride, polar, non-polar. It is polar. So what type of forces does it have? London dispersion and dipole-dipole. Yes, no, I'll discuss that in just a moment. Let me get to where I have some page.
Is that a chlorine molecule? It has 2 lone pairs, right?
Technically, it would have 3 because it needs an octet. I just didn't put all of them on there because they were the outer atoms. And a lot of times we leave the lone pairs off of outer atoms. But chlorine has to have an octet. Everybody below period 2 has to have an octet. Okay, what about tetrachloromethane? Polar, non-polar? It is non-polar. It is non-polar because all 4 groups on the central atom are identical. It is non-polar because all 4 groups on the central atom are identical. If you ever change up one group on the central atom so that you have 2 different types of groups on the central atom, you automatically make it polar. Or if you have a lone pair on the central atom, you automatically make it polar. So what type of forces does tetrachloromethane have? Just London dispersion. So I want you to take a moment. And I want you to try to come up with the next 2. I will say nitrogen dioxide is a free radical. A free radical means it has a lone electron on the central atom. It's not paired up. Okay, every intersection and at the end of the line, if there's not something showing, there's a carbon. So this one would have nitrogen, a carbon. It would have a carbon here and a carbon there. It would have a carbon here and a carbon there. Okay, so I went ahead and helped out while you were working on it. Number one, so you could check to see how you were doing. But number two, so that we can continue our discussion. So when I took the structure I gave you in black, each of the intersections had to be a carbon, and each end of a line had to be a carbon. Because this is how it is commonly notated to make it faster. And then because carbon had to have 4 bonds, it meant that if it was on the end, it had to have 3 hydrogens. And if it was in the middle, it had to have 2 hydrogens. Also nitrogen, because nitrogen must always have an octet, had to have a lone pair. The one of the few times that you run into something that doesn't have a lone pair is when you get to a free radical, such as nitrogen dioxide. The Lewis-Dot structure for nitrogen dioxide only has 17 valence electrons. In giving your outer atoms, if their octet of 8, that means you only use up 16. So you had to have a free radical. A free radical means a lone electron. But a free radical, folks, behaves similarly as a lone pair. Not quite as extensive. It doesn't have as much repulsion as with the lone pair, but it does behave similarly to a lone pair. So nitrogen dioxide is bent. What would be the structure around that nitrogen? It has 4 groups. So the electron arrangement's tetrahedral, but one of them's a lone pair. Trigonal pyramidal. So this is trigonal pyramidal, where you could draw it with something like this. And basically it forms a nice pyramid at the base and everybody connects to the nitrogen. So it is trigonal pyramidal. So they are both polar. So what are the intermolecular forces? Now, who would be the higher melting points and boiling points? Because it's a bigger molecule. Questions? Now, I wanted to bring this one in, folks, for all 5 of the, or for all 3 of these, they all have the same formula. It is C5H12. This one's actually kind of tricky to think about. Because if I were to draw just a density diagram, this one would look like a ball. This one would look like this long, huge banana. And this one would look like it's got a stump on the log. As my best explanations here. These are all non-polar because they're all carbon and hydrogen only. But, and so they all have just London dispersion and nothing else. So who of these three has the higher melting and boiling points? Is it, raised hands, A? Is it B? Or is it B? Is it, I don't know. It is B. Because it stretches out more, it's got a bigger surface area for those forces. Okay, just in the last couple of minutes, I just wanted to give you words for everything I drew. So the word three, I mean, you should already have a sense of it by now. There are 3 types of structures. The Lewis structure that you got in college chemistry 1 shows every atom and every bond. Then we did the condensed structure. That would be like having the CH3, CH2, CH2, CH3 type thing, where we didn't show the bonds, but we kind of indicated how everybody was connected. And then you had the line formula. This one was probably the newest to most of you, I suspect, the line formula. And in the line formula, the carbon represents any line intersection, and it also represents the end of the line if there's nothing showing. Hydrogens are omitted on the carbons. Your non-carbon and hydrogen atoms are shown. And they may or may not show lone pairs in a line structure. The other thing I just wanted to quickly mention, because I was asked what the difference between that, this, and that meant. This means that the bond is in the plane. This means that the bond comes at you. And this means that the bond goes behind the plane. It's a way of noting a 2-dimensional or a 3-dimensional structure in a 2-dimensional space. So basically, if I had this one I would have drawn with the dark wedge. This one I would have drawn with the dash wedge, and this one would be a line. Okay, folks, it's that time of the day. I am going to be gone Friday, but I will be in my office some tomorrow. So stop by if you have questions. If you have time, you can start the homework tonight. And that way, if you have questions, you have a chance to ask before you have to do trial 2. Hi.
I got my active chemistry code from the UCA bookstore,
Uh-huh.
and they said it's on back order.
You can go online directly through Active and get it too.
Okay.
And I'm not supposed to say this, but it's cheaper.
Well, I
But
already
if
paid
you,
for it.
okay, you've already paid for it.
Yeah.
So it's on. Oh,
It's
they
a
have-
string of letters and numbers. I don't know why it's on back order.
Yeah, I don't know either. Did they give you any indication when they would have it, since it's not a book?
Not as of yet.
Okay, well, you have 2 weeks for free,
Okay.
and then we got to get it activated. So maybe it'll come in by next week.
Okay.
If not, then I will have some folks calling up the bookstore, because that's ridiculous. I can get you a code.
Okay. Well, I just wanted to make sure you were informed on that.
Thank you.
Thank you.
So the quiz that we have to turn to you, that's,
It's okay. This is the reason I want everybody on that side.
Wait, so the quiz that we had to turn into, that's quiz 1, and that's due the 22nd?
27th.
27th. Oh.
No, we don't.
Very lost on what intermolecular forces were.
Okay, so intermolecular forces is the attraction from one molecule to the next molecule of the same type. But there's no bond. It's just,
I know she said she posted.
okay, so let's go with fun stuff. There's people that you don't want to have anything to do with. You wouldn't be attracted to them.
Mhm.
You wouldn't have any intermolecular forces with them. And then there's people that you want to hang out with. And there's an attraction between you and that person.
Mhm.
That would be a stronger intermolecular force.
Okay, okay.
Does that make
makes
sense?
Yeah, yeah.
So me and my silliness.
No, that works.
And then there's somebody that you may just really want to be with all the time.
Yeah.
And that's the strongest of the intermolecular forces.
Okay, that's making sense. That works. And you said something about the class being like blended or something?
No, it's a flipped class style. So if you'll watch the lectures before you come to class,
Mhm.
I could do problems. And this particular class requires a lot more problems than even college can one day.
Right.
So
Definitely.
watch the video lectures. So the video lecture folder in our Blackboard, watch those before you come to class. It'll make a lot more difference on getting what's going on in class.
Yes, ma'am. Okay, that works perfect. Thank you.
I was gonna say, is this online now or gonna be?
It will be, I gotta stop recording. And it takes a while. I have to wait until I get an email saying it's ready to do something with, and then I have to download it or upload it to my YouTube before I can give you a code.
Oh, no, you're
It's a
fine.
process.
It'll be like before.
But you will have it before too long.
Yeah, okay, sweet. Thank you.
Just had a quick question. You're probably gonna be able to tell. I got very confused when
It's
you were
okay.
doing this set of problems. So I was good here with the,
Mhm.
I can't remember what you said. that thing there.
It doesn't
Yeah,
matter.
that was-
Trimethylamine is what it's called, but.
And then you started drawing this and I was like, there's not a fluorine on
Okay,
that.
so
Is that what this
What the
line was?
problem, yes, that was
Okay.
what that originally
That's what I
was.
thought that
So
was.
where that carbon is,
Yeah,
was that
that's
carbon?
that. So it's
Where
carbon
it's-
there, it
Uh-huh.
bends, and then it's temperamental. And then where it bends, there's another carbon there.
Correct, and then the fluorine.
Okay.
Oh dear,
I'll-
like right
I'll go grab this.
oh, that made big friend, yeah,
Name
Oh.
tag.
it's okay,
I will
I got it.
just- I didn't ever tell you my name. Also, I'm Matt.
Hello,
It's
Matt.
good to meet you. Kind of officially. I'm very scared of this class. And
Okay,
I think I told you that at lab, but this is kind of just. me. So I'm a 8th semester senior. It's my
Okay.
spring of my senior year. I took Chem 1 spring of 2019,
okay, so right before COVID,
the spring of my freshman year.
yeah,
So it's been a while. And kind of today was like a reality check when you were like, okay, draw these. And I was like,
I will say it's better from a lot of perspectives. We won't be doing as many of these drawings after we get past this chapter.
okay, well, but
But you need to remember how, so what I'm gonna do, I
gonna
realize
email
several
you.
people needed it, so one of the
really?
things I'm gonna do is send out an email to everybody, and I'm planning to go in and put, all of my list, my, notes from Lewis structures and from VSCPR theory and from valence bond theory in a folder of extras.
okay, so we.
That
can go
way,
watch.
if people want to get some more practice or understand how I do things, they'll have all the resources.
Okay, yeah, because I was just very, like you said, that FASCR or whatever it was.
VSCPR, valence shell electron pair
Oh, it's the
repulsion.
VAM, okay. 'Cause I took Chem 1 with, I don't know if you were here and I'm.
Oh, I've
assuming
been
you
here
were,
since
assuming you're-
2006.
Yeah, so you're tenured a long time. With Dr. Yusuf,
Yes,
it was very difficult.
okay,
I barely got out of that class with my
Okay.
skin. And so I was like going back through my notes last night to kind of try and prime for
Mhm.
today. And you said that, and I was like, I didn't see that anywhere. It was just like, it just seemed like we missed some stuff. Because I tried to take Chem 2 that fall after